Hi and welcome to the second video of this channel. As I mentioned in my previous video, I'm going to talk about the binomial distribution. The binomial distribution is a discrete probability distribution. That means that you can get the probability of a discrete variable using a mass probability distribution. It is very important before we go into detail of the binomial distribution. It is very important to know what a Bernoulli trial is beforehand, because a binomial distribution is a generalized case of a Bernoulli trial. So let's define the Bernoulli trial. A Bernoulli trial is basically a random experiment with two possible results, either failure or success. That means that, for example, let's say that you toss a coin. When you toss a coin, there are only two possible results: a head or a tail. Only those outcomes. There are no more possible results. That's like the classic example for the Bernoulli trial. It also consists on repeated trials. Why? Because if you only have one trial and your experiment only has two possible outcomes, of course, the probability that you're going to get is the probability of each event is 0.5. And these repeated trials are very useful, because if you are the CEO of a company, you want to test your production process. You might be interested in taking a sample from your productions. You might be interested in knowing how many of those products has imperfections, and which ones do not have any imperfections. So it is very important in those cases you can model that scenario using a binomial distribution. Also, the probability of success is denoted by P, and the probability of failure is Q equals 1 minus P. This is just basic math, as you might know. The probability of an experiment is always 1, but the probability of each specific event is not 1. So since you only have two possible outcomes, P plus Q equals 1. The trials are completely independent from each other. That means that if you have, let's go back to the example of the coin. If you toss a coin 3 times and you get a head in the first attempt, it is not going to affect your future attempts. So if you get a head in the first one, it doesn't mean that you're going to get a head in the second attempt. So basically each trial is independent from each other. So let's go with an example. Let's explain this using an example. Let's say that you have an imperfect coin, and the probability to get a head is 0.7, and the probability to get a tail is 0.3. You're asked to toss the coin 3 times. What's the probability to get the specific scenario? Head, tail, head. Okay, in this case, well, I have listed all the possible scenarios here when you toss a coin 3 times. However, this is not like necessary, because the only probability that we want to know is the probability of this specific case, which is listed here. And to obtain the probability, we have to take into account the chain rule, which basically says that if you have independent events and you want to know the probability for all those events to occur in only one experiment, you only have to multiply the individual probabilities. You have to multiply them all. So in this case, and we already know what's the probability to get a head, a tail, and a tail, we just have to replace those values here. The probability to get head, tail, head in 3 attempts is the same probability, is the probability to get a head in the first attempt, a tail in the second attempt, and head again in the third attempt. We only plug in these probabilities, we get 0.7 times 0.3 times 0.7, and we obtain the result 0.145. This is very simple, as you can see. So now that we know this, we can start with the binomial distribution. The binomial distribution is basically the X number of successes in M Bernoulli trials. So let's say that you want to know that you toss a coin again, like the classic example, that you toss a coin 7 times, and you want to know the probability to get 4 tails in out of those seven tosses, right? You can model that experiment using a binomial distribution. In that case, then the number of tails is your discrete variable, and is also the number of successes. X is known as a random binomial variable, as I mentioned before, and the probability distribution of this variable is called binomial distribution, and the values are denoted as follows. With this expression, this is like important to know, because it's very important to know like the notation that we use to show the binomial distribution. However, it's not that important. I just wanted you to know that. And let's explain this with another example. Let's say that you are an inspector from Coljuegos, and a lot of people reported that a casino is cheating in a game that consists in tossing a coin. According to their records, they found that the probability to get head is 0.7, and you are interested in confirming these accusations. What's the probability to get 3 tails out of 5 tosses using an imperfect coin, and a perfect coin? So basically, the game consists in tossing a coin, and you will like to compare both results, right? Like the probability to get 5 tosses, to get 3 tails out of 5 tosses is in both coins. And let's use the first scenario and in this scenario we have that the probability to get a head, as I mentioned before, is 0.7, and the probability to get a tail, which is our success in this case, is 0.3. And you will, as I mentioned, you're interested in knowing the probability to get 3 tails out of 5 tosses, in which case we just follow the same example, the same procedure as in the first example. We just take like the random experiment. So I decided to use tail in the first attempt, tail tail in the second attempt, and tail in the third attempt, on head in the 2 last attempts. And we just have use the chain rule again and replace those values. So 0.3 times 0.3 0.3 times 0.3 times 0.7 times 0.7, and we get the result 0.01323. That's the probability of that specific event. But remember, in this case, we are not only interested in that specific event, we are interested in all the cases where we get 3 tails out of 5 doses. I have listed them all here. You can verify that by hand. If we get 10 possible scenarios for this situation, and if this is the probability for only one of these, we only have to multiply this probability for the 10 possible scenarios. When we do that, we use the notation here, like binomial. There is successes in five trials with a probability of success of 0.3. We multiply that and we get the result 0.1323. We can also get a general expression, so we don't have to list all the possible scenarios anymore, because imagine now it is pretty simple, because our experiment consists on a few trials, but imagine that you take I don't know, you have 1,000 trials. That's a lot of trials, and to list all the possible scenarios by hand will be very hard. Fortunately, we can get a formula, or we can obtain a formula. What's the formula? Now, let's figure it out. We have that this is our probability of success, 0.3, and we have that 0.3 is repeated 3 times, right? So what if 3 is our number of successes? So basically we can say that P, right? We can elevate P to our number of successes, which is X. So P, the probability of success, elevated to X, which is our number of successes. Now we have 0.7 twice. 0.7 is our probability of failure. 1 minus P. So we just can say, okay, Q. Q is elevated to what? Okay, so now we see that there are 5 trials, and we have here our number of successes. So we can see here that this is equals to n minus X, that is number of trials minus number of successes. So basically Q, we can elevate Q to m minus X. We obtain this expression here. I know, okay, and now how do we get all these possible scenarios? Basically what we have here is a partition. You have like a number of elements, and you are going to group them basically into sets, or 2 subsets in this case, right? One of which contains X elements, and one of which contains n minus X elements, right? And how do you calculate a partition of 2 groups? Basically with a combination, right? and choose x. That's the expression. I know that this looks like really like a nastiness. However, let's polish it. Um, let's polish it, and we have now this expression here, right? And choose x times p elevated to x times q elevated to n minus x. And remember that x is always a discrete variable, so it can only have discrete values: 0, 1, 2, etc. And now that we have this formula, we can just go ahead and calculate the second scenario, which is when the coin is perfect. That is, when a coin is perfect, you know that the probability to get head or tail is 0.5 because the coin is perfect. So we just have to replace that. P elevated to x is 0.5 elevated to 3, and q elevated to n minus x is 0.5 elevated to 2, and choose x is equals to 10, and we can calculate in 0.30, I'm sorry, we can get 0.3125. So you can, as you can see, the customers might be right, because it is less likely to win in that game if they use an imperfect coin. And just to finish, it is important to mention how to calculate the mean and the variance of the binomial distribution. It is important to know that the mean is equals to n, number of trails, times p, which is the probability of success, and the variance is equal to m times p times q. We can prove it, but I think that is not like the purpose of this course. So I just want you to know that how to calculate that, and that's it. We have finished. Thank you very much for watching this video. I hope that you find it helpful. In the next video, I'm going to show how to do this using Python. And well, see you next time, and have a great day.